we are discussing about the algebraic structures and some general properties of the algebraic systems we have read, and now based on the properties that the one set with some binary operators they are satisfying, we are defining the different algebraic systems. We have read the semi group, monoid and group, and today we will read the another algebraic structures, ring. Now, this algebraic structure ring is slightly different from the other three that we have read. Normally, the algebraic systems we have defined that one set or non-empty set with finite or infinite number of elements and a binary operator, one single binary operator defined on the set. Now, for this ring that instead of one operator that two operators will consider, and the general properties that the commutativity, associativity, closure, that multiplicate, the identity, inverse, etc., that we have read, and we will see that for the two operations defined on this ring and what are the properties that must satisfy, so that this algebraic system we can call a ring. So, a ring R is, if I give the definition, is a non-empty set of elements with two binary operations. Normally, we called addition, these two operations are addition and multiplication, but this addition and multiplication may not be our ordinary addition and multiplication. There can be two different operations, but normally we call them addition and multiplication. Such that for all elements say ABC belongs to R, the following properties are satisfied. Now, since there are two operations, so what are the properties based on these two operations that we identify? So, first thing is that this is a additive commutative group. Ring is a additive commutative group. So, we can write the ring So, obviously, since it is a group, so the property of the group, that group satisfied, that must be satisfied. So, we write the group properties, we remember that it must satisfy the closure So, since now we have two operations, so closure with respect to addition. If we remember that when we have defined the group, then we have considered only one operation. So, with respect to one operation, say the addition first we are considering. Then it should be the associative. It must hold the associativity. So, it is associative. Then the additive identity exists, and if it is a group, then there must be additive inverse also. So, additive inverse also exists. Now, it is a commutative group. So, though it must hold the commutative property. So, the commutative property holds. So, if we quickly write that closure, we remember that if A B belongs to R, then A plus B belongs to R. So, the notation we are taking that plus and star. So, the ring we are defining R plus star, as if plus is addition and star is multiplication. Now, if it is associative, then ABC belongs to R with respect to addition. So, we write A plus B plus C is A plus B plus C. Now, additive identity exists. So, if E is the additive identity, then A plus E is E plus A equal to A only. Additive inverse exists. So, we know that A plus, if A dash is the inverse of A, is A dash plus A equal to the identity. Now, if it is commutative property holds, then A B belongs to R, A plus B equal to B plus A. So, this is only the ring is a additive commutative group. In addition, the sum of the properties. So, with some additional properties, some additional properties. Now, what are those properties? So, these are only with respect to addition. So, in addition, we write it is continued the properties. Now, we remember there are two binary operators when we are discussing the ring. So, now we consider the multiplication operation. So, again this sixth property will be the it is closure property, closure with respect to multiplication. Then it is associative with respect to multiplication. Now, it is distributive in nature since we have two operations. So, now this is distributive property holds. Now, these are the three additional properties. So, since we have taken the star notation for multiplication, so if AB belongs to R, then A star B also belongs to R. Now, associative, so A B C belongs to R, then A star B star C is equal to A star B star C. Distributive property holds. So, we take that multiplication is distributive over addition. So, A star B plus C equal to A star B plus A star C, or I can write that B plus C star A, since it is okay, we write the two operations, that I can write B star A plus C star A. So, these are the three additional properties over additive commutative group that makes a algebraic system ring. This is my ring. So, I give one simple example that where this property holds. So, let Z is a set of integers R is a set of real numbers and C is a set of complex numbers. Then the two binary operators or operations defined on these sets, say Z or R real numbers or complex numbers, will satisfy all the properties they satisfy the properties just now we discussed, that the commutative group, additive commutative group, and the with respect to multiplication, the closure, associative and distributive. Now, I can write that 1 to 8 that we have discussed, and so each one, that means Z plus star, R plus star, C the complex number, plaster form a ring. And obviously, here when we are considering the complex number, the multiplication is the multiplication of between multiplication of two complex numbers or addition of two complex numbers. Now, here the addition or the additive identity is 0 and additive inverse is of additive inverse of x inverse of x is minus x. Normally we take like that. Now, we consider another example of different type. See, we consider a set of matrices, 2 by 2 matrices. So, let M to Z is the set of two by two matrices or integer matrices, that means matrices of integer elements. The two binary operations on the set are matrix addition and matrix multiplication. So, quickly we see that what is matrix addition. Two by two matrix. So, we consider the say AB, CD, plus EF, GH, and this is equal to, it is, we know the matrix addition is defined as the sum of element wise addition or the sum of elements, that means A plus E, B plus F, C plus G and D plus H. Now, how we define the matrix multiplication? If I take the same matrix A, B, C, D, now I take multiplication, then E, F, G, H equal to, we know that AE plus BG, then AF plus BH, CE plus DG, CF plus DH. This is my matrix multiplication. Now, if we see that, then I can write my matrix, or additive identity, matrix addition if we consider, then with respect to the operation addition, that 0 0 0 0, this 2 by 2 matrix is the additive identity. Since if we add element wise 0, then I will be getting the same matrix. So, this is additive identity. Then what is additive inverse? That we know that a plus a dash equal to E. That means, if I take the 2 by 2 matrix is A B C D, then my minus A minus B minus C minus D, this is equal to give me 0 0 0 0. So, minus A minus B is my additive inverse. Minus A minus B minus C minus D is the additive inverse of ABCD. So, if I now, since the element wise it is the addition and our normal addition is closure property holds. So, obviously for addition also, matrix addition also, the closure property holds. So, if I continued, so since matrix addition is the ordinary addition of elements, matrix elements. So, we can see that, so it with respect to addition, I should tell that matrix addition, the closure property the associativity and commutativity are satisfied. So, already we have seen that it is additive, that is it is matrix addition is or the set of 2 by 2 matrices with respect to matrix addition is the additive commutative group that we have seen when we have studied the this example as a example of a group. Now, what about the matrix multiplication? So, matrix multiplication, if we see, then multiplication is defined as the multiplication and ordinary multiplication and addition. So, closure property holds. So, If we consider the matrix multiplication involves ordinary addition and multiplication of elements integer, because we have considered the integer matrices, multiplication of integers. So, the closure property, the associativity, are satisfied. Now, since it is multiplication, so the multiplicative identity is sorry. Oh, we have not yet read that thing. The distributive properties we have to, with respect to multiplicative operations of the matrix multiplication, the distributive property also holds. So, it forms a ring, but one thing we observe or we notice that if we take say one example, that 2 by 2 matrix of like say 1 2 1 1 and 5 6 4 0. If I do the matrix multiplication, we get 1 into 5 plus 2 into 4, that is 13, then 1 2 6 0, that is 6, 1 1, this is 9, and again this is 6. Now, if we take the 5 6 4 0 same matrix in different order, that means AB and BA. So, 1 2 1 1, then we get that 5 plus 6, this is 11, then this is 10 plus 6, it is 16, 4 0. So, this becomes 4 and this becomes 8. So, what we see that this AB, if I consider that A is a 2 by 2 matrix and B is a 2 by 2 matrix, this is A star B, and this is we take B and A. So, this is my B star A, and these two are not equal. So, what we can conclude that the if AB, or better it with respect to my matrix multiplication, this is not equal to B star A. So, it is not commutative. So, it is not commutative. So, that means if we want a commutative ring, then we have, in addition we have to make that this property should hold. So, here actually here A B belongs to M to Z. Okay. So, if I add, then that the ring also holds. That means, if earlier we have seen that the ring holds the 8 properties, now if we give as if this is a 9th properties, that if A star B equal to B star A, that means with respect to the operations multiplication, may or may not be the ordinary multiplication. Okay. And AB belongs to R, then it is a commutative ring, then it is a commutative ring. Now, if we add some more properties with respect to multiplication. Okay. So, I see that with respect to multiplication we have considered closure, we have considered associative, and with respect to both addition and multiplication we have considered the distributive properties. But if I consider, say, if multiplicative identity exists. Okay. So, if multiplicative identity exists, that is, I can write that, say, some element u belongs to R such that u not equal to the additive identity, say E, and AU, or I should write A star U, since multiplication sign we have taken star, A star U equal to U star A equal to A for all A belongs to R. That means, one multiplicative identity exists. Another property we take, that say no zero divisors. This is one property, that no zero divisors. That means, if A B belongs to R and A star B equal to B star A equal to 0. Then either A equal to 0 or B equal to 0. Then if these all all 1 to 11 this property holds. So, if some algebraic systems, or I can tell the ring, if the algebraic system satisfy the properties one to 11, then it is an integral domain. It is called an integral domain. That means, over the properties of ring, we can add the properties of that commutativity with respect to multiplication, then multiplicative identity exist, and no zero divisors, then this becomes this is called that integral domain. Now, if I just take the example that S is a set of integers say positive, negative and 0 under addition and multiplication, ordinary addition and multiplication. Then S is a ring first, and S is the additional 3 properties also hold. So, S is an integral domain. That means, it is a commutative ring with multiplicative identity and with no zero divisors. So, we have read the mainly the definition of ring, how one algebraic systems becomes a ring, and what are the properties over the group, the other algebraic systems that we have read earlier, so that it becomes a ring. And then again the properties over ring, we have considered some other additional properties with respect to the another binary operations, that commutativity, the multiplicative identity and no zero divisors, then this is making another algebraic systems or the variant of ring, sometimes we call this is the integral domain. And we will read some examples and some more properties of ring in the next lecture, because in real life or in ring has different type of application, particularly in computer science and in mathematics as usual, that ring has a number of applications area. So, we will see some of the properties.